Okay, hello and welcome back. In this video, we're covering section 9.4, which will be our introduction to vectors. So just to give a brief introduction, we can visualize a vector as a directional line segment between 2 points. So usually use an arrow. So we can say it's starting at some point P and terminating at some point Q with this specific direction. So we can say the line going from P to Q is our vector V. So if you're writing by hand, you'll usually see this like arrow notation to denote a vector. In the text, it will use just a bold letter to indicate a vector. So I'll be using this arrow notation. So we can say this symbol will mean our vector V. And we can describe a few properties of this vector. One is what's called the magnitude, which we use this, it looks like a double absolute value symbol. And this means basically the length of our arrow, the length of the vector. And then we can also describe, if we're imagining this being in standard position, some angle that rotates up to the vector. So we'll call that the direction of the vector. So these are the two attributes that define a vector, the magnitude and the direction. And this should remind you of our work with polar coordinates, where we described some point in space using an r value and a theta value. So we're still describing the same idea. Instead of r, we have the magnitude, and the angle theta is what we're calling the direction of the vector. But we now have this sort of pointed situation, and we can use vectors to represent a lot of different properties and concepts. You might have worked with these in physics, which is likely where you'll first encounter vectors in a class outside of a standard math class. So we'll explore some of the properties of vectors, how to combine them together. We basically have a new mathematical object that we can work with. So we'll be exploring their properties and see some examples of what we can do with them. So we'll start just by looking at some visual properties of vectors. So we have, in our first example, 3 different vectors that can be placed anywhere in space. In this second example, it's showing multiple vectors that have the same magnitude. They each have the same length. And notice they're all parallel to each other. That means they have the same directional angle. We could imagine some angle here. So this would all be the same angle, the same magnitude. So these are all technically equivalent vectors, meaning the actual position of the vector isn't part of its definition. We can move them around freely in space, and as long as they have the same magnitude and direction, they'll be considered as the same vector. If we are to add or subtract vectors, just thinking about adding right now, visually that would be starting with your first vector. If we're adding v and w, you would start with your first vector, and then the second one would be placed on the terminal point of the first vector. So the sum of 2 vectors is a third vector that would go from your original starting point on your first vector to the terminal point on your second vector. And we'll define this more algebraically later on in this section, but visually this is how we can represent the addition of 2 vectors. We could also negate a vector, which will flip the angle, it will reverse the direction of the vector. You can equate this to when we negated the r value of a polar coordinate. We saw it flip to the other side of our circle. So we can get the same kind of idea here. We have some vector v, which has this magnitude and direction. Negative v would have the same magnitude, but the direction would be flipped. And so that means if we were to subtract vectors, like here we had v plus w, but if we wanted to do vector v minus w, we can view that as the vector v plus the negation of w. So that means we would still start at the tip of v, but instead our second vector w would be going in the opposite direction. So we would get some vector like this for the subtraction. And then we can also scale vectors. We can make them larger or smaller by multiplying some constant number, which in this context we'll call this a scalar. So just some number that can scale a vector, make it larger or smaller. So we have our vector v here. So 2v, if we multiply it by 2, it will double the magnitude. And here's another example of a negative reversing the direction. And then we have another definition of what we'll call a unit vector, which just means a vector of magnitude 1. So the magnitude is equal to 1, it's a unit vector. It can have any particular direction, but if its magnitude is equal to 1, we'll call it a unit vector. So let's add some more definition to our vector so we can start to do some algebraic manipulation. So let me redraw our picture. So this will be our vector v. And we typically imagine a vector starting at the origin. That doesn't have to be the case. And we'll see how to deal with a vector in some other position. But if we do this, we can imagine some horizontal line and a vertical line producing a right triangle. So the hypotenuse would be our magnitude. And then we can call this side length A and this side length B. So this allows us to describe a vector also in terms of these two distances, the lengths of the right triangle that's formed by the vector itself. So this will be what's called the component form. We would call this distance A the horizontal component, and the distance B the vertical component. So the way to notate this is to write, we use this angled parentheses. We can say A comma B, kind of like we're listing the coordinate point of where the vector is terminating if we're starting at the origin. And that means we can also produce a formula for the magnitude of our vector. Since it's the hypotenuse of a triangle, it would just follow the Pythagorean theorem. So we could say a squared plus b squared equals the magnitude squared. Or if we go ahead and take the square root, we can say the magnitude is the square root of a squared plus b squared. So this first definition is what's called the component form of a vector, meaning we're describing it using the horizontal and vertical components. They also call this a algebraic vector here too. But if our vector is not positioned at the origin, we said that a vector can exist anywhere in space, and as long as the magnitude and direction is the same, we would consider them the same vector. So if it was in some other position, so this will be our vector, write it here. So now let's say that it's starting at the position just x1, y1, some point, and then it terminates at some other point, x2, y2. Well, if we want to describe the components, vertical and horizontal, we just want these two distances. So that would make this distance x2 minus x1, and then this distance would be y2 minus y1, difference of y's. So that means we can describe our vector as x2 minus x1, that's our horizontal component, that would be our a value, and then y2 minus y1, that will be our vertical component, or our b value. So another way to define a vector, we're still just describing these two distances, but if you're given 2 points, you can use this to find your vector. So that's what we have here. Suppose that v is a vector with initial point 1, not necessarily at the origin, and our terminal point 2. And here's our definition. x2 minus x1 as our horizontal, and y2 minus y1 as our vertical component. So let's practice producing a vector from 2 points. So we have point 1, which is -1, 2. And then point 2 is 4, 6. So our position vector would have a horizontal component of 4 minus -1. Just got to be careful with the double negatives. And then the vertical component will be 6 minus 2. So that will become 5, 4. And so the text gives this theorem about the equality of vectors. We said we can move them around anywhere, and as long as their magnitude and direction is the same, we'll consider them the same vector. So we can also describe this in terms of our components. They say if we have some vector v, some vector w, then the vectors are equal if their horizontal components are the same and the vertical components are the same. All right, so I mentioned that we can add and subtract vectors together. But we need to define a couple things before we get to that point. One is writing a vector as a sum of 2 unit vectors. So we mentioned that a unit vector is a vector of magnitude 1. So let me redraw our picture. So our vector will have some horizontal component, some vertical component. The 2 unit vectors that we will use are denoted as I and j. So the unit vector I has the components 1, 0, meaning it just extends 1 unit in the horizontal x direction. And then the unit vector j is the vector 0, 1, meaning it extends just 1 unit in the vertical direction. So we can describe a vector as a sum of two. We said earlier, if we imagine some vector in this direction and we add another vector in this way, the sum of the two vectors would be the line starting at the initial point of the first one and ending at the terminal point. So we can produce two vectors that create the two sides of this triangle and add them together. So our I vector would extend 1 unit in the x direction, call that I. So to get this full side, we would just need to scale this vector by whatever the horizontal component is, meaning we can describe the whole length as a times the vector I. And j just goes 1 unit in the vertical direction. So that means this whole distance would be b times the vector j. And then if we add these two vectors together, we will get our original vector v. So we can get another definition, another way to describe a vector as the sum of two vectors. So in component form, it's a comma b. But we can also describe this as a times the unit vector I plus b times the unit vector j. And so this will be helpful later on because then we could change what our unit vectors are. We can get some kind of skewing or shifting of our whole system. And then we basically did it right here where we multiplied a vector to scale it. So let's define that as scalar multiplication. So if we have some vector, call this our vector v, and let's say we want to scale it to some larger size. Well, we multiply by some constant or some scalar. So we can describe that as some number c times our vector. So c times the vector v, well, the vector v we can write in its component form, a comma b. So the c will essentially distribute to both terms. This would become c times a, comma, c times b. Or writing it as a sum of two unit vectors, this would be c times a I plus c times b j. So we call this operation scalar multiplication because we're scaling a vector. And we'll be making this distinction between a vector and a scalar, which is some constant number. So with this in mind, let's see how we can add two vectors together. So let's say we have some vector v and w. So let's say v is a1, b1, and then w is another vector, which we'll just say is a2, b2. And if we're adding them together, Let's say this is v. If we're adding v and w, then we would place w, let's say that this vector is w, on top of v. So v plus w would be this vector, starting at the beginning of v and ending at the terminal point of w. So what would be its components? Well, we can imagine the horizontal and vertical components of both v and w. We get two right triangles. So this would be A1 and B1, and this would be A2 and B2. So what would be the horizontal and vertical component of our sum of the two vectors? We get this outer triangle. And this would just be the distance A1 plus A2. We have this first distance and then our second horizontal component. And similarly, we can describe the vertical as B1 plus B2. So that means we can describe v plus w. Its horizontal component is just the sum of the two, so a1 plus a2, vertical component b1 plus b2. Or using I and j, we can say a1 plus a2 I plus b1 plus b2 j. And similarly for vector subtraction, if we did v minus w, we just need to subtract their corresponding components. So this would be a1 minus a2 and b1 minus b2. And we can use this other form as well. So now we have some formulas for vector addition and subtraction, as well as scalar multiplication and how to find our magnitudes. That's what we have here. Given some vector v, some vector w, we have our sum of two, so we're just adding the two components. Subtraction of two vectors, subtracting the two components. Scalar multiplication is distributing that number to both components. And we saw earlier to find the magnitude, we got that from the Pythagorean theorem. So let's practice combining some vectors together. So in example 3, we have our first vector v, and I'll write it in component form 2, 3. And our second vector w is 3, negative 4. So first let's add them together. v plus w should just be 2 plus 3, 3 plus negative 4. So that will give us 5, negative 1. And then for subtraction, so v minus w, this should just be 2 minus 3, 3 minus negative 4. So those will end up adding together. So we'll get negative 1, 7. So we can do combinations of adding and scalar multiplication. So let's look at two vectors again. I think these will be the same two. Let's just rewrite this. So 2, 3, and vector w is 3, 4, or 3, negative 4. So let's find in part A just 3 times v. So we're scaling v by a factor of 3. Well, that 3 will just distribute to both terms here. So we should get the vector 6, comma 9. And then we can find something like 2 times the vector v minus 3 times the vector w. So it would be 2 times 2, 3 minus 3 times 3, negative 4. So let's scale both of these vectors first by distributing that outside term. So this will be 4, comma 6. And the second vector, I'll keep the negative and just put the 3 through. So this would be 9, comma negative 12. So we're subtracting these two vectors. So this should give us 4 minus 9, comma 6 minus negative 12. Which should be negative 5. And then 6 plus 12 will be 18. And then part C wants us just to find the magnitude of vector v. So that would be the square root of 2 squared plus 3 squared. Or the square root of 9, or 4 plus 9. Or root 13. We're really just finding the hypotenuse of some triangle that has a bottom length of 2, side length of 3. And this would be our magnitude. So something else we might be asked to do is to find a unit vector that's in some direction, in the same direction as another vector. So let's redraw our picture again. So some vector v. We have a horizontal and vertical component, and this will be our magnitude. So if we want to scale this down so that its magnitude is equal to 1, we can just divide or multiply the vector by 1 over its magnitude. Like if we wanted to change 4 into 1, you would want to divide it by 4. You want to divide it by the same magnitude of the number. So same idea here. If we want to scale this back to just have a magnitude of 1, we can multiply by 1 over the magnitude. So they usually write a unit vector using a u. So this unit vector would be the vector v divided by its magnitude. Or we can write it as 1 over the magnitude times the vector. And that's what we have here. So let's see an example. We want to find a unit vector that has the same direction as vector v, which is 4, comma negative 3, or 4 minus 3i. 4i minus 3j. So first let's find the magnitude of our vector. This would be the square root of 4 squared plus negative 3 squared, which will be the square root of 16 plus 9, which is root 25, which will reduce just to 5. So that means our unit vector in the direction of v would be 1 over 5 times the vector. So we would get 4 over 5, comma, negative 3 over 5. Or using I and j, we could say 4/5 I minus 3/5 j. So we have a vector in the same direction as v, but scaled so that its magnitude is equal to 1. So we can also describe a vector, I mentioned at the beginning, using just its direction and its magnitude. So we'll have our vector v again. So this will be our magnitude. And then we have some direction, so some angle. This would be our distance a and b. But let's say we don't know a and b, but we know the magnitude and the direction. Well, we can use the sine and cosine to create expressions for a and b that just involve the angle and the magnitude. We can say the cosine of our angle is the adjacent side over the hypotenuse, so a over the magnitude of b. And then solving for a, we get that a is equal to the magnitude of v times the cosine of theta. If this feels familiar, it should, because we did something very similar with polar coordinates when we were converting it from rectangular and polar descriptions. We said x equals r cosine theta. So we're doing the same thing here, just kind of with the different labels. So let's do the same thing for b using the sine. We can say the sine of theta is the opposite side over the hypotenuse, so b over the magnitude of v, which means that b is equal to magnitude of v sine theta. And so since we've been describing v in component form as a comma b, we can also replace those with magnitude of v cosine theta for the horizontal component and the magnitude of v sine theta. And then since they're both multiplied by the magnitude, we can pull that out in front as a scalar in front of our vector. So we could say magnitude of v times cosine theta, comma sine theta. Or in I and j format, we can say magnitude v times the cosine of theta times unit vector I plus the sine of theta times unit vector j. And this might remind you of our polar form of a complex number, where we had our r, which is the magnitude in our case here, times some statement with cosine plus sine. This is a different I. It's not our imaginary number. It's the unit vector I. But we have a similar kind of setup here. So if we were just given the magnitude and direction, we can still describe our vector in component form or in I and j form. So our last example, we got two more. This one is a word problem, so let's see how we can describe this using vectors. It says a ball is thrown with an initial speed of 25 miles per hour in a direction that makes an angle of 30 degrees with the positive x-axis. So here our vector is representing initial speed, like initial velocity. So we can say its magnitude is 25 miles per hour. And it's forming this angle, theta here, which is 30 degrees. It wants us to express the velocity vector in terms of I and j. And then it asks us what is the initial speed in the horizontal and the vertical direction. So for us, the magnitude of our vector is 25 miles per hour. Our angle is 30 degrees. So that means we can describe our vector. We want it in I and j format. So it will be magnitude times the cosine of theta times vector I plus the sine of theta times vector j. So for us, that would be 25 times the cosine of 30 degrees I plus the sine of 30 degrees j. The cosine of 30 degrees is the square root of 3 over 2. That's pi over 6. And that would make the sine 1/2. So let's just distribute the 25 through. That means our vector is 25 root 3 over 2 I plus 25 over 2j. So we're breaking up our initial velocity into some horizontal and vertical component. This would be our horizontal, and this would be our vertical. Since we're describing velocity, this gives us how fast it's moving horizontally and how fast it's moving vertically as it's moving in this diagonal direction. So let's answer the question more directly. It asks for the horizontal initial speed that's 25 root 3 over 2, or approximately 21.65 miles per hour. And then our vertical initial speed that is the 25 over 2, or about 12.5 miles per hour. Or no, this would be exactly 12.5. So using this vector notation, we can split up some force or velocity, in this case, into its horizontal and vertical components. Our last example just has us find the angle of a vector, the direction, given its description. So it says vector v is 4i minus 4j, or in component form that would be 4 minus 4. So we can imagine visually where this vector will terminate. 4 minus 4, that would put it in the fourth quadrant. So we want some angle that terminates in the fourth quadrant. And we can treat this like finding the angle of a polar coordinate. If you recall, we used the tangent. We can say the tangent of theta would be, in this case, the b value divided by the a value. So negative 4 over 4, which is negative 1. So we want the angle that has a tangent value of negative 1 in the fourth quadrant. That should be the pi over 4 angle in the fourth quadrant, because yeah, the two side lengths are the same. One is positive, one is negative. So theta should be 7 pi over 4. It's our pi over 4 angle in the fourth quadrant. So very similar to finding the angle of a polar coordinate. Alright, that will be it for this section. So we looked at some visual representations of vectors, described the component form and how to find a position vector. We added and subtracted some vectors algebraically. We found scalar multiples and the magnitude of a vector. We reduced a vector to a unit vector in the same direction. And then we described a vector in terms of its direction and magnitude. There's some additional examples in the text on modeling with vectors, which are more like physics-based applications. So if you're interested, there's a lot of cool examples of how these could be applied to some physical situations. So we have our definition of vectors. We'll see some further operations in our next video and what we can do based on something called the dot product. So we'll pick up there. That'll be it for this video, and I'll see you next time.